All right. I feel very underqualified to talk about Gödel and why you believe that. I saw that quote from Gödel in the preface to Robinson's second edition of nonstandard analysis. So he actually, there is a 2-paragraph quote of his which he gave after Robinson's talk in 1973, and that whole 2-paragraph was published in the preface. So I have those 2 paragraphs, maybe I think in the 3rd slide. But I want to start with some other things. So I have a couple of audio clips, and I have them transcribed up here. And they might seem completely random right now. This is not even math. This Alan Watts is someone who might be familiar to people who follow maybe spiritual videos on YouTube and so on. So this is clearly not math. The second audio clip I will have is more mathematical. It's from a documentary about Gödel and 3 other mathematicians. And then I'll show you Gödel's quote, and then we'll start talking about that. Let me see if I can play this audio.
All these redundancies of talk. We talk about seeing sights, hearing sounds, feeling feelings. All that is irrelevant. There are sights, there are sounds, there are feelings. You don't feel a feeling. The feeling itself already contains the feeling of it. You see? That's very simple. To have sight, you don't need something to be seen on the one hand, and a seer of something to be seen on the other. And then some mysterious way they come together. The seer and the seen, the knower and the known, are what we call terms. Terms mean ends. And they are what in mathematical language are called limits. Now, when we take a stick, the stick has its 2 ends. They are the terms of the stick. But the ends of the stick do not exist as sort of separate points which encounter each other on the occasion of meeting in the stick. They are actually abstract points. The ends themselves, considered as themselves, are purely geometrical. They're Euclidean imaginations. The reality is the stick. Okay?
Right, so he's talking about how we do not really see the true reality, right? So when we say something is the end of a stick, it really is a lot of things there, and then we just associate with all of them the term end, right? So he uses the mathematical term limit, maybe not in the sense we use limits, but it's kind of similar in imagination. Now, in preparing for this talk last week, I wanted to understand how would have Gödel been thinking. So I searched what are some documentaries people have made about Gödel. Unfortunately, there are not too many. There should be more documentaries made about historical mathematicians, especially from recent past. But I found this one called Dangerous Knowledge, which is not about only Gödel. It starts with Cantor, and then Boltzmann, and then Gödel, and then Alan Turing. So it starts with Cantor's continuum hypothesis, or rather other things about Cantor, but then continuum hypothesis somehow becomes one of the key things in the documentary. And Gödel was also thinking about the continuum hypothesis. So I'll play this clip.
My son used to say that he came here to make me into a
Actually, in the documentary, they talk about how when Cantor was developing his definition of real numbers and then the set theory that emerged out of that work, he used to say how he is getting these visions from God, and that is what is motivating him to write about it. And then once the continuum hypothesis was formulated, and then they could not prove or disprove it. At that time, they did not know that it could not have been proven or disproven from the other axioms. Cantor would keep trying to prove it. So there have been times where he thought he had proved it, and then he realized he had not proved it, and then he thought he had disproved it, and then he realized he had not disproved it, and eventually he was just, the later part of Cantor's life was just stuck in that feedback loop of proving and then disproving the continuum hypothesis. However, here what this clip is talking about is how certain things can be, or at least they believe that certain things could be known, not logically, but intuitively, right? So Gödel, in some of his philosophical beliefs about mathematics, which I'll get into in a minute, would believe that even after the continuum hypothesis was known to be unprovable or independent of ZFC, which happened within Gödel's lifetime, he still believed that either it is true or not true, in a sense that he believed in a sort of Platonism about mathematics, right? So for him, there was a true, quote-unquote, true mathematical universe in which either it is true or not, and all that the independence result showed was that we cannot learn about that truth by logic. We'll have to use some other types of mathematical intuition to realize whether it should be true or should not be true. So that's the sense in which they're using the word intuition. So, and sorry, I'm using my laptop. So this is Gödel's statement, and this is the two-paragraph statement that was published in Robinson's second edition, not first edition. So he says, I would like to point out a fact that was not explicitly mentioned by Professor Robinson. So this is happening after Robinson's talk at IAS, Princeton. But seems quite important to me, namely that non-standard analysis frequently simplifies substantially the proofs, not only of elementary theorems, but also of deep results. This is true, for example, also for the proof of the existence of invariant subspaces for compact operators, disregarding the improvement of the result. And it is true in an even higher degree in other cases. So what he's referencing is that around that time, Robinson and Bernstein had solved some conjecture of Halmus and someone else, I'm forgetting, where it had to do with some problem in functional analysis, and they solved it in an even stronger generality, which is why he said disregarding the improvement of the result. So not only did they prove the conjecture, they proved a stronger form of it. This state of affairs should prevent a rather common misinterpretation of non-standard analysis. Namely the idea that it is some kind of extravagance, I can't say that word, or fad of mathematical logicians. So remember, this is happening in 1973. This is just over 10 years after Robinson's book. So at that time, this was one of the beliefs of mathematicians, that it's kind of a fad of the logicians. Incidentally, it might still be like that belief even now, 50 years later. But that's how it was then. Rather, there are good reasons to believe that non-standard analysis in some version or other will be the analysis of the future. One reason is the just mentioned simplification of proofs, since simplification facilitates discovery. Another, even more convincing reason is the following. Arithmetic starts with the integers and proceeds by successively enlarging the number system by rational and negative numbers, irrational numbers, etc. But the next quite natural step after the reals, namely the introduction of infinitesimals, has simply been omitted. I think in coming centuries it will be considered a great oddity in the history of mathematics that the first exact theory of infinitesimals was developed 300 years after the invention of the differential calculus. I am inclined to believe that this oddity has something to do with another oddity related to the same span of time, namely the fact that such problems as formals, which can be written down in 10 symbols of elementary arithmetic, are still unsolved 300 years after they have been posed. Perhaps the omission mentioned is largely responsible for the fact that compared to the enormous development of abstract mathematics, the solution of concrete numerical problems was left far behind. So he thinks it's a great oddity that it took us 300 years to really truly formalize infinitesimals after they had already been used in mathematics and then sort of abandoned once we figured out how to do calculus with real numbers that Cantor and Dedekind had invented. In my opinion, it would be considered an even bigger oddity that even after having discovered this, we still did not actually make it more commonly understood, right? So in some sense, we are disrespecting our whole history of mathematics by still teaching our students that calculus is defined in this one way, the standard way we define calculus now, and that any student like Sarah who might have had natural intuitions about infinitesimals, they are just being dismissed. So again, in preparation for the talk, I searched online for what other people are saying about this. So there is a post on history of the Stack Exchange for History of Science and Mathematics. The question about what would Gödel have meant. So I guess this is, oh, what's happening? How do I was trying to zoom in and then you rotated.
It looks better.
It looks fine. Can you read it? It's very small. Okay.
There you go.
So let's see. So there is the first answer. So someone named Gordon quotes Zeilberger suggesting a particular way of how Gödel's prediction might come true. So continuous analysis and geometry are just degenerate approximation to the discrete world, like Alan Watts was saying the first time. While discrete analysis is conceptually simpler, technically it is usually much more difficult. Continuous mathematics is an approximation of the discrete one in contraposition to the traditional point of view. Under this approach, the notion of a very big finite set is very important, and the definition of a hyperfinite set in nonstandard analysis is an appropriate formalization for this notion that satisfies the modern requirement to mathematical rigor. Okay. Then he goes on to say, so this quote is about Gödel's realism, where he thinks there is one true mathematics. And so despite their remoteness from sense experience, Gödel is saying we do have something like a perception of the objects of set theory, as is seen from the fact that the axioms force themselves upon us as being true. I don't see any reason why we should have less confidence in this kind of perception, in mathematical intuition, than in sense perception. So for Gödel, the same way we have sense perception, we have mathematical perception, and that is what he actually thinks is mathematical intuition. And through that mathematical intuition, you can sort of intuit which axioms should be true, and maybe the current axioms of set theory kind of force themselves upon us because we feel they are true in some sense, and so we start working with them. Of course, logically, once we fix them, we work with them very logically and we remove all emotions out of it. Now, this other answer by Mikhail Katz, who is a very well-known historian of nonstandard analysis. So if you ever search history of nonstandard analysis or philosophy of infinitesimals, you will come across his papers. He says in the 1970s, Gödel recommended Robinson for membership in the British Academy of Sciences. I checked, Robinson never got that membership. his recommendation was based in part on Robinson's framework for analysis with infinitesimals. From the viewpoint of Gödel's realism, the significance of Robinson's work was to extend further the ordered number system beyond the natural, integer, rational, and real numbers, so as to include the hyperreal numbers. Robinson, for his part, did not subscribe to realist views about set theory. So Robinson's philosophy of mathematics was actually different from Gödel's, and wrote explicitly that he did not view set theory as a foundation for mathematics. In private correspondence, Gödel chastised Robinson for expressing views contrary to Gödel's realist ideas about number systems. To Gödel, the significance of Robinson's work was to be able to give precise mathematical formulation in currently acceptable foundational frameworks to Leibniz's ideas about infinitesimal and infinite numbers. Both Robinson and Gödel actually liked Leibniz's philosophy, even though they disagreed about whether they believe mathematics is real or not, precisely. I'm stuck on this screen now. Right, so I then started looking up what were Gödel's philosophical beliefs about mathematics. So on the Stanford Encyclopedia, there are a couple of sections for his rationalism and realism. Realism is what we have been talking about, and for rationalism, so it says Gödel's rationalism has its roots in the Leibnizian thought that the world, not that which we immanently experienced, but that which itself gives rise to immanent experience, is perfect and beautiful and therefore rational and orderly. Gödel's justification rests partly on inductive generalization from the perfection and beauty of mathematics. I think I'll skip because I will be running out of time. We already have seen a little bit of Gödel's realism. So Joel David Hankins recently had this fantastic article published a couple of years ago, where he argued how if our historical development of calculus had been a slightly different, had happened in a slightly different way, then we might have had continuum hypothesis as one of our fundamental axioms. And the way he argues this is that he says that all the mathematical structures that are kind of needed for our basic mathematical theories, we like those structures to be well described. So in technical terms, we want them to have some sort of what is called categoricity, meaning we can specify what they are up to isomorphism. So real numbers up to isomorphism is the set of real numbers is the unique, completely ordered field up to isomorphism. And that definition only, we got that definition only in the late 1800s, like 200, 300 years after the development of calculus. We had to come to that definition because we were trying to then understand calculus without appealing to infinitesimals. And so we defined Cantor and Weierstrass were able to define some set of, in different ways, their own sets of real numbers, and then we had this categoricity results that they are both isomorphic. We would have felt a similar need to have a categoricity result for the hyperreals if we truly had hyperreals as in our foundation of calculus, which could have happened if Newton and Leibniz just said things slightly bit differently. They could have said that there is a realm of real numbers. They don't have to say what the real numbers are. Like at that time, people were intuitively talking about numbers without formally defining them. So they could have said there is a realm of real numbers and there is a realm of hyperreal numbers, which has more numbers, and the infinitesimals exist in the top realm, not the bottom realm, and it would also take care of some of the philosophical criticisms that people were having at the time about how can these infinitesimals be smaller than other numbers while still being a number. It would just be in a different plane of existence, so to say. In that way, if we had developed calculus that way, then later on, 300 years later, when it was time to rigorize, quote-unquote, rigorize mathematics, and develop all these axioms for mathematics, we would have come across the continuum hypothesis as a fundamental axiom, because we would have seen that with it we could prove that there is a smallest hyperreal, there's a unique smallest hyperreal field, and without it we could not prove it. And once we would have realized that continuum hypothesis would have become one of the axioms, and later on, if Cohen would have proved that negation of continuum hypothesis is still consistent, we would have just seen it as an oddity of mathematics, just like we see negation of continuum, negation of axiom of choice as an oddity, right? So that's how history could have developed, and it talks about the contingency of our mathematical beliefs, the historical contingency of our mathematical beliefs. And this is the paper of Robinson and Bernstein, where they proved that result about compact operators. I think Halmos and Smith's original conjecture was about squares of operators, but they proved squares of compact operators would leave some subspace invariant or something like that, and they proved it for all polynomials of compact operators. I might be actually misrepresenting the result, because I was just saying without reading the abstract, and I put these slides a few days ago. So excuse me, but I wanted to just indicate how nonstandard analysis has been used in research, but I want to switch to the final part of the talk, where I want to talk about the context for right now, because Gödel said that statement 50 years ago, and a lot of mathematical results have been proven with nonstandard analysis since then. And even now, most mathematicians are not aware of what it is. And maybe they are becoming less aware. I have met mathematicians, older mathematicians, who all really studied it routinely in the 80s and 90s, but now we don't study that. Alright, so Peter Loeb's article in 1975 is the most important article for me, because it allows the use of nonstandard analysis in probability theory, which is what I do. So it allows us to use standard measure theoretic results in non-standard spaces. And after that work, just a huge amount of work started happening in probability theory and mathematical physics and so on with non-standard analysis. So the first book is really comprehensive. At that time, it was in the 80s. There is this. There are like tons of applications in economics. Even now, I think, so this Robert Anderson, he is quite old, but he still works and has even recent papers in mathematical economics using non-standard analysis. And there are quite a few economists right now who are working with non-standard tools. Somehow it's used a lot in economics. Isler and Fajardo wrote this model theory of stochastic processes, which is also related to non-standard analysis. And then Loeb and others edited this non-standard analysis for the working mathematician, which has a lot of applications to all sorts of any area you can name, there can be applications of non-standard analysis there. And of course, Isler wrote this calculus text that Rob said, mentioned, and then Isler's PhD student, Kathleen Sullivan, did an experiment in, I think, local Wisconsin high schools where they compared students' understanding of calculus using Isler's book versus using standard books at the time in 1976. Of course, the non-standard framework seemed to be beneficial in lots of ways. Students had, in a sense, better grasp of their understanding of calculus using that, but that were the finding of her results in her PhD thesis. But of course, really no big widespread studies happened, and it's unsure if it's going to happen unless someone really motivated joins a psychology of education PhD program and gets an IRB for something like this. So we'll see. And then, of course, this is Rob's article, which I found a few years ago, and I felt seen by that article, and I was at that time considering not doing mathematics anymore. It was my first postdoc. I actually applied to philosophy PhD programs. I got rejected, and that's why I'm still doing mathematics. There's a really curious state of affairs here mentioned in this stack change answer where Ed Perkins, a really well-known probability theorist, he said somewhere that he noticed that some of the theorems were originally derived using nonstandard analysis. He really liked nonstandard analysis. And I have standardized the arguments to make them more accessible. This saddens me a bit, as I feel that the non-standard view, clumsy as it is at times, is pedagogically superior and allows one to come up with novel insights, like Gödel was saying. It facilitates discovery. So it's a really curious state of affairs that it really helps us in our research, but then it's kind of harder to publish that because most mathematicians do not understand it. They don't have that in their formal training in grad school. They don't get trained in logic, and so they don't understand how logic is used. So I'm kind of out of time, so maybe we can do some of these reflections while in the discussion. So there are three themes when I reflect on this. There are three themes I think about, which is what's the epistemic value of non-standard analysis, so the value in it facilitating discovery, the things we know. And then epistemic injustices, like the injustice that I think happened to Sarah when we standardized our foundations, and then she had some intuitions that could have been validated, but were just not, and then she would be getting B- in calculus and would think she cannot do mathematics. But in fact, I think she was quite artistic and had really nice intuitions at her age without having been exposed to hyperreals. And then, do we as mathematicians, when we teach calculus, do we have not just, is it not just a nice thing, but is it an ethical obligation, a stronger statement, to tell our students about how this history unfolded so that they can make their own beliefs about mathematics and how mathematics is used to describe reality. So when I applied for these philosophy schools, I had to write a writing sample. And so I ended that writing sample with this, and I'll sort of end my talk with this also, although there is another slide which is just one line. So here it says about 50 years ago, so I'm writing this, about 50 years ago, Martin Davis and Ruben Hirsch had concluded their article on non-standard analysis in the Scientific American as follows. So they say, perhaps as with other radical innovations, the full use of the new ideas will be made by a new generation of mathematicians who are not too deeply embedded in standard methods to enjoy the freedom and power of non-standard analysis. Right? So, of course, maybe two new generations have come up since 50 years ago, but that did not happen. Unfortunately, more than 50 years later, we are perhaps still looking for a new generation of mathematicians to take us out of the deep embedding standard methods that we have found ourselves in. And the socio-cultural conditioning at the heart of this embedding is still as strong as ever. So a lot of this deep embedding standard methods is really the socio-cultural conditioning. We are conditioned to believe in the real numbers because that's in our standard textbooks. So I wrote, one of my papers I have what I call a philosophically motivated introduction to non-standard analysis. It's intended to be very accessible. I wrote somewhere there that understanding non-standard analysis effectively seems to require one to fight against years of unconscious socio-cultural conditioning within their mathematics careers. And therefore, I believe that philosophizing about what it is that we are studying is helpful in not succumbing to the intellectual harmful effects of that conditioning. And so really, the future that Gödel prophesied has not happened yet, but maybe we can look to the next generation to think more about these things. Although it's unlikely because philosophy of mathematics is apparently not as funded as it was 50 years ago. So Peter Loeb, who has personally influenced me a lot, he died in 2024, but in January 2024 there was a session in honor of 50 years of Loeb measures, and he had prepared a speech at the beginning of that session, and one sentence or two sentences in that speech where he was saying, don't let the skeptics make you think any different. You know what you have. And he was speaking in really, big terms, and he was speaking in grand terms that he was not making very explicit. Like when he says, you know what you have, he was not saying what you have or what you know. But he was generally talking about this, the strength of non-standard analysis is my interpretation, because he was talking about the skeptics. There are lots of skeptics of non-standard analysis even now, which is really irrational for a community like the mathematicians who are supposed to be logical and rational. So I think I'll just stop here, and we can have discussion.